Hello, today we'll be solving problem 5.23, in which we must find the magnetic vector potential of a finite segment of straight wire carrying current I, and we'll put the wire on the z-axis from z1 to z2 and use equation 5.66, which I have listed below, and then we must check that our answer is consistent with equation 5.37. And so to be able to check that it's consistent, we'll need to use this magnetic vector potential to find the magnetic field. So to the top right, you can see a diagram of the situation. We have our script vector, and then you can see our wires going from Z1 to Z2. And so the first thing we can do is rewrite our script vector. The magnitude of it can be written as the square root of Z squared plus S squared, where S is the radial distance from the Z-axis to the point we're trying to find it at. And so then using that, we can rewrite our magnetic vector potential as mu naught I over 4 pi, and then this is going to be in the z-hat direction because that's the direction of our current, and our integral will be going from z1 to z2, and then we'll have dz because dz is going to equal to dl here, the square root, and then that'll be all over the square root of z squared plus s squared. And now for this part, we can just use the identity that the integral of 1 over the square root of x squared plus some constant a squared dx is going to be equal to the natural log of the absolute value of x plus the square root of x squared plus a squared. Or you can solve it yourself using a trig sub. I'm just going to not do that in this problem because this is focusing on the physics and not the mathematics of this problem. But you're welcome to do that yourself if you'd like. So when we use that identity, we can then rewrite this as mu naught I over 4 pi, still in the z-hat direction, and then we'll have ln of, the absolute value of z plus the square root, absolute value of z plus the square root of z squared plus s squared. And then this will be evaluated from z1 to z2. And then plugging that in, we'll get mu naught I over 4 pi z hat, and then ln of z2 plus the square root of z2 squared plus s squared, and then minus ln of z1 plus the square root of z1 squared plus s squared. And then we can just use the basic properties of logs and just rewrite this as mu naught I over 4 pi ln of z2 plus the square root of z2 squared plus s squared over z1 plus the square root of z1 squared plus s squared in the z-hat direction. And this is actually our answer to the first part of the question, but now I must verify that it's consistent with 5.37, equation 5.37. So we need to find the magnetic field, which we can do by taking the curl of this vector potential. And so the nice thing about this is that the only variable is our radial variable s, and we only have a component in the z-hat direction. So that makes our curl easier, and it'll just be equal to the negative partial derivative with respect to s of our potential vector, magnetic potential vector, and this will be in the phi-hat direction. And then this is then going to be equal to the negative partial derivative with respect to s of, I'm just going to actually rewrite it. We're just going to plug in, rather than using this, I'm just going to plug in this because it will be a bit easier just algebraically. So I'll just copy that down to here to save a little bit of time. And then, again, this will be in the phi hat direction. And, whoops, I am forgetting that we should have our constants in the front. So I'm just going to bring those down as well. And there we go, almost. All right, I'm going to bring that negative in front, and there we go. All right. So now to solve that, we can use the chain rule, and we'll get negative mu naught I over 4 pi, again in the phi hat direction, and then we will have, using the chain rule, we'll have 1 over z2 plus the square root of z2 squared plus s squared, because we basically, the derivative of like ln of x, for example, would be 1 over x. So we take 1 over the inside of the ln, and we bring that in front, and then we're going to take the derivative of, so we, now we have to find the derivative of the inside and then multiply that. So that is going to be, we'll get 2s over 2 times the square root of z2 squared plus s squared, and then we can see our s, or sorry, our 2's cancel out, which is nice. And then we'll do the exact same for the second term. So we'll have 1 over z1 plus the square root of z1 squared plus s squared, and multiply that by 2s over 2 times the square root of z1 plus z1 squared plus s squared. Yeah, all right. And then the next move to simplify this, first why don't we actually take this s outside and we'll put this here. And then we're going to want to multiply this by, I'm just going to put it down here, but we're going to multiply it by the z2 minus the square root of z2 squared plus s squared, and then over z2 minus the square root of z2 squared plus s squared. So really we're just multiplying it by 1. This is going to help us simplify, basically. And we're going to do the exact same over here, so it'll be, multiply it by z1 minus the square root of z1 squared plus s squared over z1 minus square root of z1 squared plus s squared. And for the sake of saving room, I'm just going to make these a bit smaller. And then when we rewrite this, we're going to get that this is equal to negative mu naught I s in the phi hat direction over 4 pi, and then we'll have z2 minus the square root of z2 squared plus s squared over, when we multiply it out, we're going to have z2 squared and then minus z2 squared, and it would be plus s squared, but that negative gets distributed, so we will have minus s squared. And then this will still be multiplied by 1 over the square root of z2 squared plus s squared. And then we'll do the same for the second term. So now we'll have z1 minus the square root of z1 squared plus s squared over z1 squared minus z1 squared minus s squared multiplied by 1 over the square root of z1 squared plus s squared. And some terms that cancel again, so these go away and these go away, and we can actually pull out our negative s squared, so that will get rid of that negative and we'll have s squared on the bottom, and then that can cancel our s on the top. So there we go. And then we get to say, then we'll have, this will be equal to mu naught I over 4 pi s in the phi hat direction. And now we can multiply these two together, right? So we'll get z2 minus the square root of z2 squared plus s squared over just the square root of z2 squared plus s squared minus z1 minus the square root of z1 squared plus s squared over the square root of z1 squared plus s squared. Alright, and now we can, we'll just basically be separating out these two. So we'll have z2 over the square root of z2 squared plus s squared, and then we'll have minus basically these two over each other, so that'll just be 1. So we can rewrite this as mu naught I over 4 pi s in the phi hat direction, and then we'll have z2 over the square root of z2 squared plus s squared, and then minus 1, because square root of z2 squared plus s squared divided by the square root of z2 squared plus s squared is just 1. So minus 1, and then minus z1 over the square root of z1 squared plus s squared, and then it'll be minus 1, but our negatives will distribute, so we'll have plus 1. And then that, good, and these negatives will, or these 1s will cancel. So then we can rewrite this as mu naught I over 4 pi s, and then we'll have z2 over the square root of z2 squared plus s squared, just rewriting stuff now, minus z1 over the square root of z1 squared plus s squared. And this will be in the phi hat direction. And now, if we go back to our diagram, and it's asking us to verify equation 5.37. And for that, we can say that theta 1 is going to be this angle here when we go, when we are going to z1 all the way to theta 2. And so theta 2 would be this whole angle. And you can use, just using trig, we can see that sine of theta 1 would be equal to z1 over the square root of z1 squared plus s squared, and sine of theta 2 would be z2 over the square root of z2 squared plus s squared. And you can see that just because this whole length, if this is basically like the origin, that would be z1, and then this will be z2, so that works. And yeah, so then we can just plug those into our equation, and we get that b is equal to mu naught I over 4 pi s times sine of theta 2 minus sine of theta 1 in the phi hat direction. And this is the same as equation 5.37. So we are good. It has been verified, and there is your solution. Just box it up here. All right.